Think we're live? Hello everyone! Welcome to the OneClass channel. My name is Millan, and I am a software engineering student at Carleton University in Ottawa, Canada. Today, we will be going over some commonly asked physics questions at both the high school and college or university level. If you need help with your homework or if you're interested in tutoring, check out the links in the description below. Cool. So, I'm going to just switch my screen over real fast, like that, and we can learn about the physics. Physics is always a fun time. Okay, so the first question that we got on the menu today is, the question says diameter of the Earth, but there's a little attached image here that says diameter of Earth. So let's just call that diameter, D, E, Earth. Makes sense to me. That is equal to 12,756 kilometers. Another way that we could write this, we know that K for kilometers or kilograms or kilonewtons, any K, you know that is equal to 10 to the power of 3. So we could also write this as 12,756 times 10 to the 3 meters. That's another great way to represent this. Sometimes it's good to convert everything to base units. So you take all the K's for kilo or M's for milli or capital M for mega. It's always good to convert those into just numbers so we have base units. Otherwise our units are going to be a little bit more uncomfortable to deal with, but it's still possible. Anyways, just my little suggestion that I have. And the question is asking the approximate area of cross-section of Earth. Cross-section of Earth containing center. Here in Canada, we write center RE, but sometimes you'll have center as ER. Why? English, that's why. That's just the way it's going to be. But anyways, let's kind of draw out what this is. So if this is the globe, and just to draw that's the equator. And maybe out here we have its rotation of axis or axis of rotation. Okay, so we know the Earth is a globe, and we can kind of say that it's a perfect sphere. For this question, we kind of got to approximate it as a perfect sphere, but in reality, it's a little bit thicker around the equator and a little bit, it's kind of more obloid or elliptical shape. But don't worry about all of that stuff. So a cross section would really just be like if we were to chop out a circle that contains the center. The center, let's call that C. Starts with C, center. Makes sense to me. We're pretty much trying to find what the area of that little circle in the middle of the globe is going to contain. Now we know that since it is in the middle, we know that the radius here, R, is going to be the same in all directions. R can go down, and we're always going to find the same R distance from the center to any part of the sphere. Okay, so it doesn't matter if our cross-section is basically in line with the equator, or if it's more of if our cross-section is like this, more with a meridian, for those of you who are geographically inclined. If we did a meridian, we should come to the same conclusion under the assumption that the Earth is actually a perfect sphere. Okay, so We know that the radius is always going to be the same. That means the diameter is always going to be the same as well, because I guess RE is equal to, or 2 times RE is equal to DE. 2 times the radius of anything is going to be the diameter of the same thing. And it's definitely going to apply in the case of this globe as well. And if we wanted to find the cross-section, well, we know the cross-section is going to be a circle. The cross-section of any sphere has to be a circle. So this is really just a situation where we're trying to find the area of a circle, which is fairly straightforward. So know that A for area of a circle is equal to 2 times pi times r squared. Okay, we don't have r directly, we have it indirectly from DE. So we know that, whoa, it's a little bit too much zoom, you know. Zoom is still a cool thing to use though, great for video calls, if you're gonna go for less than 40 minutes, if you're free. Anyways, yeah, so let's get our r value from our d value. So r is equal to 1/2 of dE, or let's say RE, radius of the Earth. Yeah, we're all talking about the Earth, so we're going to use Earth. So we know, wait a minute, that is not the right thing to be writing. It's going to be 1/2 times dE, that's RE. So there's going to be 1/2 of 12,756 times 10 to the 3 meters. Pulling out my handy dandy TI-84 calculator, my favorite calculator on the planet. So we got 12,756 times 10 to the power of 3. Divide that whole thing by 2, and we get the radius of the Earth is equals 6,378 times 10 to the 3 meters. And that looks pretty reasonable, like 6,000 compared to like just over 12,000. Yeah, it looks about reasonable. So to get the area, let's send that through the area equation. Area equals that whole thing squared. So it's going to be 2 times pi times 6. Whoops, that's not a good looking 6. 6,378 times 10 to the power of 3 meters. Square that whole thing, and let's ask the calculator what that is. Hey calculator, what is the answer to that? Will you tell me? Of course you will. So the area, whoa, let's bring it back here. So the area is equal to, this is going to be an approximated answer. So the question gave us 5 significant figures. So we'll also we'll have 5 significant figures for our final answer, just so we have like the same degree of precision. So 2.555, looking like a movie phone number. 5559, and that would be 5 significant digits times 10 to the 14, and that's meters squared. Square meters. So the only units that are in our entire area calculation is the meters over here. That's the only unit, so it's just going to be meters, but you got to send it through the square, so meter square. Square up, buddy. Yeah. Man, I'm tripping. The area of a circle is definitely not 2 pi squared. You know what? I was thinking of about the circumference. My bad. This is a huge mistake. This is a crash the boat type situation. So it's pi r squared. So Just get rid of this term. So it's actually going to be this whole thing divided by 2. My bad. I'm tripping. Yeah. Yeah. So it yep, that's a clear oversight. This is why you don't want to be going off the top of the dome for calculations. So it is 1.277 or 2780 times 10 to the 14 meters squared. Now that definitely should be that looks reasonable in terms of the magnitude, because we have such large units. So I do have some concerns that they just didn't convert that to meters. So the unit does not agree here. So yeah, but yeah, look to your equation sheets, because sometimes you'll make ridiculous mistakes like I did there. You definitely don't want that, but you know, it's all good. The above solution has the wrong units. Should convert the radius to meters if the final answer is going to be in meters squared. Okay. Yeah, and that's it for that question. Cool. Okay, so the next question that we got on the menu today is how do we find the relationship between linear velocity and angular velocity? Well, first let's take a second and let's actually draw out like what these things even mean. Okay, now for this particular thing, let's just assume that we're going to have a constant linear velocity and a constant angular velocity, because if you have variable velocity or variable angular velocity, it makes things a lot more complicated, like, you know, second, third year college, university difficulty, but not impossible. It's just you know, let's just assume that they're constant. Okay, so this is important for circular motion. Circular motion is when you want to start using angular velocity stuff. So angular velocity and circular motion are tightly related. Okay, so imagine this is the center. The linear velocity would be like this. Suppose you're like in a car and you're driving in a loop. The linear velocity would be what you see on your speedometer. So if you're driving in a circle, typically you'll have it in like a distance divided by a time, meters per second, kilometers per hour, miles per hour, that type of stuff. Feet per second, another one. So so this is our thing here. If our distance from the center to there is r, our velocity v, this is our linear velocity. Of course, this is just at a particular moment of time, because we're actually going to be, you know, to follow the turn, our velocity is going to have to change. But just as linear velocity is like, imagine you're a car driving in a loop. That's what you see on the speedometer. Now the angular velocity is represented by a Greek letter named omega. It does look like a W, But it's very improper to call it W. It's omega. Yep. And because omega starts with O and O's look like W's, yep, that makes sense to me. So this is our angular velocity. And angular velocity is essentially at telling us what is our change in angle per unit time. Typically, we'll have it as radians per second. This will maybe be like meters per second or kilometers per hour, something like that. But angular velocity is almost always represented as radians per second. Radians divided by seconds. Radians is essentially how we're going to measure the angle. And, imagine we are in a car driving around a perfect circle. Okay, here, let's say this is our starting point. Start. And suppose our end point is here. This is our end. And if we took like, we see like this is pretty much 90 degrees or pi divided by 2 radians. So if we were to travel this in 1 second, we would have like pi over 2 radians per 1 second. And that would be our omega value, if that was the case. Now, you can kind of see like there has to be some type of relationship between the angular velocity and the linear velocity, because like if we're representing the same system of maybe a car driving around in a circle, like what you see on your speedometer is going to be the linear velocity, but it would have to take like someone who knows the exact angle that you're at to do the angular velocity stuff. Now, how we convert between them is with this equation. So linear velocity is equal to radius multiplied by omega, which is angular velocity. Okay, now does this make sense? Yes, it does. Now let's think about how we could adjust these different parameters. Parameters being like different elements of this equation. I'll actually write it out in symbols first. So linear velocity is typically represented with something like v. Radius, r, makes sense. Angular velocity, omega. All of these letters make sense. Yep. So let's think about this. If you have like a small circle, like, maybe the size of a CD, to get around this entire loop, like if you did the whole 2 pi radians around, if you did that in 1 second, that would be 2 pi radians per second. Your linear velocity is going to be something. But if you have the same angular velocity going 1 whole revolution around, but you have a smaller circular thing like you see this bottle, the base of my water bottle, this has a smaller radius than the CD. So if you were to go, this has also a smaller circumference because it has a smaller area. So if the radius is bigger, the linear velocity is also bigger if we have the same angular velocity. You see kind of how this relationship works? So they are perfectly proportional to each other with the constant that is difference between them being the radius. So bigger radius with the same angular velocity, you're going to have a bigger linear velocity. Now, if we have the same linear velocity, you have like a big loop, like let's say the whole Earth. That's a very big loop. So that's a very big r value. If you're driving like 10 kilometers per hour, it's gonna your angular velocity is gonna be quite low, because the way that you change your angle, along with your like coordinate chart, is gonna be quite slow. But if your circle is much smaller and you have a small r value, maybe just like around a roundabout, if you're driving at 10 kilometers per hour around a roundabout, your angular velocity is gonna be quite high, because you might go around the roundabout like 5 or 6 times in a couple minutes. That's going to be a much higher angular velocity as opposed to driving around the whole Earth. So this is just nice little things that you can think about to help you kind of visualize the relationship between angular and linear velocity, and they're especially useful for circular motion. And also don't think that it has to be like a complete circle for these to apply. If it's just like a small section of the circle, kind of like a pizza slice, the same things applies, as long as the radius of that path is like a subsection of a circle. Okay. Also talking about some things related to RPM, which is revolutions per minute, and radians per second. Those are pretty much the same thing, different ways of measuring angular velocity. Same way that we can have meters per second, kilometers per hour, miles per hour. We can do the same thing for angular velocity, but it's typically going to be a lot more useful to do this stuff in radians per second and meters per second, just because those are base SI units. Okay, and base SI, drop the base, base is the saving grace. Alright, so the above solution is correct. Okay, so the next question that we got is, what is the velocity equation? Kind of related to the previous question. Velocity, let's think about like how we would measure velocity. Velocity also means is related to speed, but as a vector value. And a good way to remember that is velocity is a vector and speed is a scalar. Okay, that's first letter can kind of tell you what it is. Okay, so the classical definition for velocity or speed, or let's think about some of the units that we measure speed in. Like we know that we got like meters, we got like meters per second, we got like miles per hour, we got maybe not equals, maybe we got like kilometers per hour, all different ways that we can represent speed. It always seems that to measure speed, we have some measure of distance on top, meters, miles, kilometers, divided by some unit of time. Meters per second, that'd be second. It could be hours. It could be years, if you're really, really slow. That the unit can really give us good clues about what the process is to calculate it. Okay, so we're going to basically need to have some distance over time is equal to our velocity. Okay, now it could be like the distance you travel, and that would be how you do like average velocity. So I could say like change in distance over change in time. That would be average velocity. And if you want to get a little bit more deeper into it, if you're more mathematically inclined and you're like calculus, you would want to do instantaneous velocity. So, if you're driving down the street, you're not necessarily gonna be going at the same speed all the time, right? You got stop signs, traffic lights. You're not gonna start at 100 kilometers per hour as soon as you start your car. Like, your velocity is gonna change. So to get your instantaneous velocity, which is just your velocity at a single point in time, instead you're going to want to take the derivative of, with respect to time, d over dt. That's how you represent derivative with respect to time of your distance function, equals instantaneous velocity. Distance functions are typically represented as x of t, and this is the time derivative. Okay, so velocity, speed, is pretty much just trying to say like it is how much distance you cover within a certain period of time. Now this is for linear velocity. We also got angular velocity. Which, instead of linear velocity, how it's like distance over time, it's your angles. It's your change in angles. This is typically important for curved motion. If you're moving along curves or if you're moving in a circular path, it'll be more useful there. Angular velocity, linear velocity, this is measured in, is represented with the letter V. Sometimes you'll have it as a V vector, just like if you're specifying like, hey, I'm going a certain velocity in whatever direction. Like, you got to specify the direction. Like, I could say I'm moving 10 meters per second, but if I'm moving 10 meters per second towards you, away from you, upwards, downwards, you got to specify the direction, just to be a little bit more precise with the information that we're supplying. Angular velocity is largely the same thing, except we're going to have angles. So it's going to be change in angle. Angle is typically represented with theta. Divide that by the change in time, and this will give us instantaneous. Nope, not instantaneous. This will give us the average velocity. Average angular velocity. Okay, now exactly similar to how we have in our linear thing, we have like change in distance, change in time, and we have like change in angle versus change in time. To get the instantaneous version, we're going to want to take the time derivative of the distance or the angle function, right? Because like, let's say you're driving around a roundabout, that could be like an angular velocity situation. You're not necessarily going at the same speed at all times during the roundabout. You got your yield signs that might make you slow down. Your instantaneous angular velocity is not necessarily going to be the same at all points. So you would want to do the same process, except you do the time derivative of your angle function. This would be instantaneous. Angular velocity. Okay, so our instantaneous angular velocity, our instantaneous and our average are very similar in terms of how they are processed for angular as well as linear, but we just gotta stay ready to do both of them. Doing them with the changes or with the derivatives, depending on the situation. Okay, so I think they explained it pretty good, but whoa, my bad. Just hit my microphone real fast. The above solution is correct, but be improved with mention of derivatives to find instantaneous velocities. Cool. Super duper cool. Okay, next question that we got on the menu today is, how do we calculate the mass of the sun? Now, the process that we have in the junior tutor's explanation so far, I actually very much like this example. It's gonna basically use what we know about forces and centripetal forces and gravitational forces, and we're gonna apply that to like circular motion, and it's gonna be a really cool example. Okay, so I'm gonna draw a couple circles to kind of represent what in the world we are talking about. More like what in the universe, or what in the solar system are we talking about? Okay, so in the center here, we got the sun. A whole big distance away, we got the Earth. We're not going to worry about the other planets. We only worry about the Earth and the sun, because that's just the way we like to do things. And we know that the Earth is traveling in a fairly circular pattern. Now, it's not a perfect circle. Let's just pretend that it is for approximations. We will almost always do a lot of approximations and stuff like that in physics. Like, we're making models here, and models are always wrong, but at a certain point, the amount of wrong that we are is acceptable. Like, if someone says, how tall are you? Oh, I'm 6'2" or whatever. They're like, hey, you should give me a more accurate answer. You're 6.2 and 6 millimeters. To a certain degree, we can accept a little bit of imprecision. Okay, so and we know that how long does it take for the Earth to go around the sun? Well, it depends on the year, right? No, not quite. It actually takes about 365 point. I think the calculation that they used here, they used 26 days. Days per revolution. Okay, a reason why it's why we have leap days actually is because it's because of this little extra little bit, that 0.25, because it's more than just 365 days to go around. So adding another day every 4 years helps to reduce the impact of this term. I don't know if it's exactly 2.6, but there are some like special rules about leap years. Like I think 2000 was not a leap year, so if the year is divisible by 2000 was a leap year. If it's divisible by 100, it's not a leap year unless it's divisible by 400 as well. Regardless, this is our revolution. This is our period of rotation. Okay, so this is our period of rotation, and the period is represented by the letter T. Why? Good question. Our period is 365 days, 0.26 days. Multiply that whole thing, like, let's try to get it into seconds, right? Because, base SI units are our friend here. I'm actually going to move this whole thing around just a little bit. Just over here, so we got a little bit more space. And then to convert this into seconds, well, we know a day is made of 24 hours, right? So we got like 24 hours per day. Day here neutralizes the day down here. How many minutes are in an hour? We got 60 minutes in 1 hour. So the hour down here neutralizes the hour up there. And we got 60 seconds per minute. I'll just leave it as S because that's a typical symbol for seconds. Divided by 1 minute. So the minutes down here neutralizes the minutes up there. Okay, so for T, our calculation is going to be 365.26 times 24 times 60 times 60. And I'm going to trust the junior tutor here just to save some time because we're running a little bit behind. And that's going to be about 31 million seconds. So 30, 31, 5, 5, 8, 4, 6, 4 seconds. Okay, that's how we find the period. And we know that if we have the radius, we can find some other great things. But given that we have the period that it takes, the time that it takes, we can use that to help us find the angular speed or the angular velocity. Okay, so the angular velocity is the first is the frequency is equal to 1 over t. So how long you take to do something, the reciprocal of that is how many times you're doing it per second or per unit time. And we know that 2 pi times f is equal to omega, and omega is the angular velocity. So we can multiply this whole thing by t, by 1 over t. So 2 pi divided by t is equal to angular velocity. Okay, so we can calculate this, or we can sub in our t value, 31.558.464 seconds. I guess the unit up here is radians. And that will give us our angular velocity. So that the change in angle that we're going to make. So so let's say if we go back to the diagram, if we start here, if we get to like the one way around, or it's basically just going to tell us how much of our angle is going to increase every second. That's what the angular velocity is telling us. So this would be 1.99 times 10 to the negative 7 radians per second. Okay. And we know that, let's just say that the Earth has a constant distance away from the sun. And we know that constant distance is going to be r. We would want to search up like the distance between the Earth and the sun. So that is that number. That is 1.496 times 10 to the 11 meters. That's r. Just gonna write that a little bit cleaner. Quite a far distance. I know it takes about 8 minutes for light to get from the sun all the way to here. So, interesting stuff. So for this system to remain constant, we know that the gravitational attraction of the Earth towards the sun, let's call that Fg, has to be exactly equal to the centripetal force. Has to be exactly equal to the centripetal force that is like stopping the Earth from, flying off into space. If the sun suddenly just, said, see you later, I don't exist no more, the Earth would just continue to go down a straight path. The velocity of the Earth, as is in a circular path, is always accelerating. Right? Because the velocity, at this point, the v, is there. And we know that the acceleration is the change in velocity with respect to time. So if the velocity is going, as time passes, velocity is going to go more towards the left, towards the down, towards the right here. Like, the velocity is always changing. So there has to be an acceleration that is causing this velocity to change. Without an acceleration, the velocity is staying constant and it's going in a straight line. That is not really what's going on here. So the force that is causing that velocity to change, or the acceleration that is causing that velocity to change, is gravity in this case. But the way that we can calculate it is that we know that it would be the same as a centripetal force, which is like the force supplied, like for circular motion, it's the force that causes something to go, to maintain its circular path. That's stopping it from going in a straight line. Okay, so we know that F centripetal is equal to F of gravity. We know that the centripetal force is equal to radius times omega squared times the mass of, in this case, the Earth. So it's whoever is doing the orbiting or doing the circling, that is the M that you use for centripetal force. And the force of gravity caused by the sun on the Earth, we're going to use the official equation. So that is, we're not just going to use mg, we're going to use capital G, mass of the Earth times mass of the sun divided by r squared. Mass of the sun, ms, that's what we're really looking for in this equation, or for this problem. Okay, so let's actually do some quick algebra to isolate ms so that we can input our numbers and calculate it real fast. So we're going to multiply both sides by r squared and divide both sides by big G and me. So that actually, before we even do that, we know that we can cancel out me from both sides. If we just divide both sides by me, they neutralize each other. So they will no longer be relevant to this equation or to this relationship. Okay, then we just got to multiply both sides by r squared to neutralize the r squared on the bottom of the right side, and divide both sides by big G to neutralize the big G on the right side. So we're going to have r times r squared, that's r to the power of 3, r cubed, times omega squared, whole thing divided by G. And that is equal to ms. Now, we calculated our omega value to be 1.99 times 10 to the negative 7 radians per second. And we know that our r value is 1.496 times 10 to the 11 meters. G, that's a constant that is frequently used. So let's actually write all of these values out. So r is equal to 1.496 times 10 to the 11 meters. Omega, that's equal to 1.99 times 10 to the negative 7 radians per second. And that makes sense because your angle does, like, that's a very small number, closer to 0 than anything else. And that kind of makes sense because your angle doesn't change that much with every passing second. So, you know, it seems reasonable. And G, big G, that's a constant, the gravitational constant, 6.67 times 10 to the negative 11 meters cubed divided by kilograms second squared. Okay, so sticking these into the equation, we should be able to get our value. So the r is going to be 1.496 times 10 to the 11 meters. That whole thing cubed. Don't forget those exponents. Here we have 1.99 times 10 to the negative 7 radians per second. And down here we have 6.6. Oh, that's whole thing is squared. Don't forget that. That's equal to the mass of the sun. And downstairs, 6.67 times 10 to the negative 11 meters cubed divided by kilogram second squared. Now, if we look at the units, we can see that the meters cubed down here will neutralize the meters cubed upstairs, and the per second down here will be, or the per second squared down on the upstairs will be neutralized by the divide by second squared on the downstairs. All that's going to be left is a kilograms on the downstairs here, but that's really just going to be on the upstairs of the fraction. So at the end, the unit will just be in kilograms. Okay, now let's send this through the calculator and see what we get. 0.496 times 10 to the 11 cube it. Don't forget the cube. Multiply that by 1.99 times 10 to the power of -7. Don't forget that negative. It's important to have a little bit of negativity. Just kidding. 6.67 times 10 to the power -11. And my calculation for mass, yep, we set up with the same equation, came to ms, mass of the sun. I got 1.9878 times 10 to the 30 kilogram. Okay, so that's within the same ballpark as the one given by the junior tutor here, which is reasonable because like we may have just had some different rounding stuff, so within a certain tolerance of error they are the same. Okay, now let's confirm this by actually, if we Google mass of the sun, hey, it looks very, very close. So we know that this is a pretty legitimate method to calculating the mass of the sun. Sounds good? Cool. Yeah, the above solution is good. Okay. So, the next question that we got on the menu today is, how do we calculate the mass of the Earth? An easy way that we can do this is if we know a couple of, of things about gravity. Okay, so we know that the force of gravity, Fg, is equal to big G times m. There's just two mass values, but we have a capital and a lowercase just to specify that they're different, over r squared. Okay, we also know that acceleration due to gravity, ag, is about 9.8 meters per second squared. Okay, and another way that we can get the force of gravity that's a little bit less direct is Fg is equal to mass times gravity. Okay, so this equation down here and this equation are pretty much like related to each other. They're kind of like cousins, but this one is only for Earth. But the top one, that's the more general one. So let's say you take a journey up to the moon. The mass of the moon is much smaller, so you're going to have a smaller force of gravity here. So the r in this case is going to represent the radius of the planet, or whatever. I guess the moon is not really a planet, but r is the radial distance between yourself, or the second mass, and the center of mass, or it's the distance between the center of mass. The distance between the center of masses of the two things. So that's what the r is. Distance between the center of masses of the two bodies. In our case, because we know that this is the equation for gravity on Earth, we know that the distance r on Earth, like the distance between my center of gravity and the center, or my center of mass and the center of mass of the Earth, is essentially the radius of the Earth. So a way that we could do that is, like, if we just Google radius of the Earth, So the R is equal to 6,371 kilometers, which is also equal to R equals 6,371 times 10 to the 3 meters. It's always good to convert to base SI. Yeah, so if we equate these two FG equations to each other, FG equals FG, we know the left side we can do mg, and the right side we can do gmm over r squared. We see that we have an m term that multiplies on both sides. We can neutralize. We can just like remove those from the equation, because if we just divide both sides by m, both of those will be neutralized. And then we just want to isolate that big M. That'll be the mass of the Earth. So we can have gr squared, whole thing divided by capital G, and that will give us M, which is the mass of the Earth. We know G, that's the acceleration due to gravity here on Earth. We know that that is 9.8 meters per second squared. We know that R, that's the radius of the Earth. The distance between my center of mass and the center of mass of the Earth is the radius of the Earth. And we know that that is 6,371 times 10 to the 3 meters. That whole thing is squared. And we're going to divide that whole thing by capital G. And we know that capital G is 6.67 times 10 to the negative 11. And the units are pretty intense for that one. I'm not going to write them out, but we just know that this will give us a kilogram answer. Okay, so if I send this to the calculator, times 6,371 times 10 to the power 3, square that whole thing, and divide that by 6.67 times 10 to the power negative 11. We get mass of the Earth, the mirth, is 5.963, just about that much, times 10 to the 24 kilograms. That's pretty heavy. A lot heavier than I am. But is this right now? Why didn't we just Google mass of the Earth directly? Because that would be way too easy. Yep, so we are like very, very close. The order of magnitude is the same, times 10 to the 24, and 5.9 or so. Like, this is close enough to be like acceptable as an answer. Okay, what's more important is like the process at which we found this. We found this by equating our two different equations for gravity here on Earth. And, you know, we had to know the radius, but once we know the radius, we can equate that and use that to help us find the mass of the Earth. Exciting stuff. Exciting stuff. And I guess here they just used like the F, but that would probably come from an mg calculation. So it's good, but could be improved. With including the relationship F equals mg for the F in the final equation. Now, would it be easier to just Google the mass of the Earth if you're ever asked that? Yes, but Life I know is that easy. Cool. So the next question that we got on the menu today is how do we convert from pounds to newtons? Okay. Now, we first got to discuss something. Okay. Now we typically say like, oh, I weigh like, I weigh about 180 pounds. We're kind of like saying, oh, you weigh 180 pounds. But weight and mass are not the same thing. We have gravity acceleration. That multiplied by our mass is equal to our weight. Weight is a force. It is not a mass. Now, this is where things get a little bit confusing, okay? So we know that like this would be like our A, this would be our M, and this would be our F. F equals MA. Thanks, Newton, for figuring that out for us. Okay, now weight is measured in like newtons. This would be kilograms. This would be meters per second squared. Okay, now a pound. Now we know that we typically think of like, okay, a pound is how heavy something is, right? Like if I weigh 180 pounds, if I ask a European friend, they're gonna be like, oh, I weigh like 80 kilograms. It's actually a little bit confusing because if you say you weigh in kilograms, it's not actually right. You should say that your mass in kilograms is like 80 kilograms. So weight as a force is lb. Now if we were to go backwards to the F equals ma, the gravity acceleration, the Americans like to use, or not just Americans, but people who use the imperial system, but mostly Americans, they like to use feet and stuff like that. So it's actually feet per second squared for them. And you know what they use for mass? It's a unit called slug. I'm not joking. Slug. So if you ever hear someone say like, oh, how much what's the mass? And they say slugs, like just know that you have to multiply it by feet per second to get the pound force of that. Meters per second squared, the gravity on Earth is 9.8 meters per second squared. And that's equivalent to 32.2 feet per second. Okay, so we know that 1 Newton, or we actually have like calculators that do this for us perfectly. Like we know that like one pound is equal to 4.45 newtons. Okay, things are quite confusing because here it's saying pound mass. This is another complication that we have to deal with, is that typically we use pounds for force. But a pound of mass, or a pound mass, is also referred to as slug, I think. So pound mass, 1 L. I'll do like a subscript F for pound force is that many newtons. 1 pound mass is like a similar number, but in terms of kilograms. So it's 4.5359 kilogram. Yeah. So um, we do have, the world is a strange place where sometimes we have lb for pounds and we think about mass, but it's actually a force. Like, things could be a lot easier if we all just agreed to use the same unit, but you know, keep in mind that a pound force is a pound of force is about 4.45 newtons. That's what I found on Google. So I mean, the solution here is a little bit different. Yeah. The 4.45 newtons is lb a force, not 4.41 newtons. More specific info on weight, mass, and acceleration would be helpful. Pound mass versus pound weight. Okay, so yeah. Okay, next question that we got on the menu today is, what are the units of momentum? Okay, so momentum, the equation of momentum is P. Yep, P is the letter that we use to symbolize momentum. Why? Yes, that's why. P is equal to mv. This is momentum. This is mass. And that's velocity. Okay, this is the equation on how you find momentum. Now, momentum is particularly useful for when you're dealing with collisions of stuff, as well as like the more formal equation for Newton's second law. But the question just asking for the units of momentum. Now we know that momentum or mass is going to be, in base SI we have kilograms. So P is equal to like kilograms. Oops, let's make that a square bracket. And velocity in base SI is going to be like meters per second. So instead of like using base SI, let's like abstract this into using like just the quantities that they represent. So momentum is really just mass times distance all over time. Okay, now you would typically write it as like, let's say we have a 5 kilogram bowling ball and we're bowling. The ground has no friction, let's assume, and we're bowling on a skating rink, and we bowl the ball, and it's moving at 5 meters per second. The momentum is equal to 25 kilogram meters per second. Okay, so units of momentum is you're going to have mass times the distance, all of that divided by a time. Typically kilograms, meters, and seconds if you're in SI. Slugs, feet, and seconds if you're, more of the imperial math. But yeah. Yeah, you could also use grams or whatever other types of measurements or units that you want to use for mass, distance, and time. Whatever floats your boat, as long as you keep track of what what units that you use. So the above solution is correct. Cool. Okay. Next question that we got today is how do we calculate the average speed of an object? So average speed is, well, what units measure speed? Well, we got miles per hour, meters per second, all of those different types of units for speed. But we always know that speed is going to be distance divided by some unit of time, like meters per second, miles per hour, kilometers per second, centimeters per year if you're very slow. So to calculate the average speed, you want to take like 2 points. So average speed you need 2 points of interest on path. So the first one, you're gonna have like d1, distance 1, and the time that you were there, time 1, and you're also gonna want a second point, maybe d2, and the time that you were there, t2. To find your average speed between there, you would use this equation. It's pretty much just finding like the slope between those 2 points. Thinking about calculus right there. So the average speed would be, it's your distance divided by your time, but on the top it's be more accurate to say the change in distance over the change in time. The delta, that Greek letter, that triangle, represents the change. So it's really just final minus initial, because t equals 0, that could be like the beginning of time. But if we were using that type of convention for measuring time, it might be better to, you'll have to do t2 minus t1, because you can't just do like t2 itself, because that's not going to be like that's not going to cover the time elapsed between the 2 points of interest. Okay, so you're going to do d2, the second distance point, minus the first distance point, d1, over t2 minus t1. Yeah, it really is that simple. So if we had like a position function like this, basically the velocity vector, average speed is going to be like the slope of a straight line between these 2 points. Now that is not going to be completely accurate, because if you see here, you're going to go a little bit faster because that's a little bit steeper, and here you're going a little bit slower because it's a little bit less steep. But they kind of average out to be like a straight line between them for their speed. Okay, so that would be how you find your average speed. And they came to the same conclusion here, or the same equation. It's just calculating the slope. So if you're more into the calculus, the instantaneous velocity, you'd find the derivative, because that's really just telling you the slope at a certain point. So cool. The above solution is good. Okay. Next question that we got on the menu today is, what is 1 Newton? So a Newton is a unit of force? Believe it or not, it was named after Isaac Newton. Now, Isaac Newton had this famous equation. The second, Newton's second law is F equals ma. So the force in Newton's is equal to a mass times acceleration. And if we look at the units of that, we know the mass, or for a Newton, is actually equal to a kilogram for mass multiplied by the SI version of acceleration. So that would be meters per second squared. That just, and the second squared, that really, or meters per second squared is equal to meters per second. That means your velocity, which is measured in meters per second, is changing every second. So, gravity has an acceleration of 9.8 meters per second squared. So that means that your velocity is going to increase by 9.8 meters per second every second. And I guess just to show that those are equal to each other, meters per second multiplied by 1 over second. That's just another way of writing this part. You'd see you get meters per second squared. Cool. So what this is basically telling us is 1 Newton of force is what it takes is the amount of force for 1 kilogram of stuff to have its velocity increased by 1 meter per second in 1 second. Okay. I guess you can also just as valid, like you would write it out like Newton equals kilogram meters per second squared. It's also equally valid to write it as kilogram meters times second to the power of -2. If you make an exponent negative, it just brings it to the opposite side of the derivative. So sometimes it might be difficult to draw fractional units. So doing something like this is perfectly valid to get around that. Okay, sounds good. So that is, above solution is correct, but it does not have to be accelerating a mass starting at rest. It can have a non-zero initial velocity. Okie dokie. That's a Newton. Isaac would be proud. Thanks, Isaac. Okay, so the next question that we got on the menu today is, what is a velocity versus time graph? Typically when you have something versus something else graph, this will be your y-axis and this will be your x-axis. Okay, so the dependent variable, the thing that depends on the independent, comes first. Independent. Okay, so if here is our dependent, we got velocity. Draw a little graph like that. Okay, and here we have our time. Our velocity could be changing over different points of time. Maybe something like that. Okay, so there are some properties, like, of course, your velocity function or curve is not necessarily going to look like this, but your velocity is always change. It could be changing, it could be constant. So you see here, like, this is constant. Here is like a constant decrease. And here's like a constant increase. And here is just a lot of variation. So, where it's like constantly increasing, imagine like you're in a car. That could be just like, you press down on the gas pedal and you speed up at a constant rate, or for the constant decrease, like you're putting your foot on the brake and you're slowing down at a constant speed. And on the constant section, that would be like, if you're on cruise control, your velocity is going to be constant. Now for like these really curvy sections and the velocity is changing a lot, that would be like, if you're in a car and like, you're doing a little tap dance on the gas and the brake pedal, so your velocity is changing in a very sporadic, spontaneous way. Definitely don't try that at home. Don't tap dance on your car's pedals. But if you were to do that dangerous move, you would come up with a velocity time graph that might look like a little bit something like this. Okay, now some interesting things that we can learn about a velocity time graph is the slope, the instantaneous slope. Slope is the acceleration. So in this section right here at the front, where it's constantly increasing, the slope is going to be constant as well. That means your velocity is increasing at a constant rate. Makes sense to me. When your velocity is constant, the slope is 0. That means there's no acceleration, and that makes perfect sense. Velocity can't change when there's no acceleration. My bad, excuse me. And when it's constantly decreasing, of course, it's kind of like a deceleration or a negative acceleration. And where it's really curvy, you would want to find the derivative to find the instantaneous acceleration at that point. So like when it's sloping up, you're increasing the speed or the velocity, and when it's going down, you're decreasing the velocity. Okay. Now, a very fascinating thing is that the area under the curve this is the total displacement or distance traveled. Just be super precise with that. Yeah, displacement. Displacement and distance are not the same thing. If I run in a circle, I'm gonna cover the distance, which is the circumference. But if I run in a circle and end up exactly where I started, my displacement is 0. Displacement is the distance that you are away from where you originally started, but only as like a direct path. Like a circular path ending up in the same spot has no displacement because you end up exactly where you are when you started. Okay, now it is possible that your velocity becomes negative at some points. So V for velocity. Here we got time. So if your velocity, followed like a sinusoidal pattern, remember it's distance underneath the curve, like, that, or the area underneath the curve. So that's going to be there. But under this section of the curve down here, between those 2 points, there is no area under the curve. There's only an area over the curve, right? So over the curve is negative under the curve. So you would actually like negate this stuff. So subtract. And this is like stuff you add. You only add areas that are under the curve. And areas that are over the curve, you subtract them. Basically, it's just like area between yourself and the x-axis or the horizontal axis. In this case, it's t. But like if your velocity was following a sinusoidal, like in these section, like between these two dots, your velocity is going to be negative, right? It's below the 0 line. So that means you're actually be like moving backwards. So you could see like how your displacement could be 0 if you do have negative velocities. Okay, so the area underneath the curve, you'll see more of that when you do integration and that type of stuff. That is all the area underneath, or the integration, that will be the displacement that you cover for your velocity time graph, and the derivative to get the instantaneous slope, that's how you get the acceleration. So all this calculus stuff is quite important when you, especially when you're talking about displacement, velocity, and acceleration, all very related to each other. So yeah, the above solution is good. With mentions of acceleration from the velocity time graph. Cool. So yeah, I would say that is pretty much correct. Okay, next question that we got on the menu today is, what is friction? This is friction. Hear the sound of my hands rubbing on each other? Friction is a force that opposes the motion of things. Opposes motion. If you really zoom in, you'll see, well, in physics there are 4 fundamental forces. Forces. The first, we have gravity, which is probably a force. I'm not saying that because I don't know. I'm saying that because the scientific community doesn't really know if gravity is a force or not. But, you know, we can, yeah, physics is an incomplete field. There still needs to be a lot of work done to find all the answers to the universe. We have gravity, we have electromagnetism. We have the strong force, strong nuclear force, and the weak nuclear force. Now, electromagnetism is the one that is responsible for friction. Okay, strong and weak nuclear, those, kind of like the name suggests, are only really related to nuclear physics. Gravity, you know, makes things fall. That will you'll see in like day-to-day stuff. For typical, unless you're doing nuclear type reactions, you're probably not going to worry too much about the strong and weak nuclear. But definitely the gravity force and the electromagnetism force, those are quite important. And electromagnetism, like all applied forces, any force that is not gravity is electromagnetic, if you really zoom into it. Okay, so why friction works in the first place is like everything in the universe is pretty much made up of like atoms and molecules and that type of stuff. Okay, so I'm just drawing circles to kind of model like you know, atoms and molecules. Like if we have you know, two surfaces rubbing against each other, they might even have, like this one that I drew on top is quite smooth, but it could be like a little bit rougher. Like maybe on the top we have glass and on the bottom we have like sandpaper. You know, two different surfaces. Which one has more friction? It's going to be like sandpaper, right? Because I mean, that's just like intuition of like having experience with those different materials. But if you zoom in, like really zoom in, you'll see that like the surface of sandpaper is very like bumpy and ridgy. So like there's more there's more of an ability for the atoms and molecules that make up a material like sandpaper to exert an electromagnetic force on whatever is rubbing across it. So electromagnetism is really just like the attraction between atomic particles that are really close to each other. Okay? So it's kind of like a nice diagram to say it is like this. So there's always only like one force of friction, and the direction of the force of friction is always opposite to direction of motion. So let's say we have, we have a skateboard. We got a person on the skateboard. Happy person. If their velocity is going forward, velocity, their friction, the frictional force that the wheels of the skateboard make with the ground, or the inside of the wheel and the friction that it makes with like the axle, that is going to cause like a net friction force to go backwards. Okay, now how do we calculate the frictional force? The frictional force, let's call that FF, F for force, F for friction, is going to be the coefficient of friction. That's typically represented as a mu, coefficient of friction, multiplied by the normal force. The normal force in this case would be the force that Fn, that's the force that the ground pushes back up on the skateboarder, and it is perfectly equal to the Fg, or F gravity in this case. But if you have like slopes and stuff, Fn, or the normal force, is not going to be equal to the force of gravity. So in those type of situations, you will need to do some like cosine and sine type math, but now there are different coefficients of friction for whether you are moving already or not moving already. So we have mu s, and this is static friction. And FF, we could also have UK, mu K, not UK, United Kingdom. That's a country. Yep. Static friction, we also have kinetic friction. Kinetic friction is typically going to be lower than static friction. Static friction is like if you're not moving, you might have like, if we have like glass on sandpaper, like the atoms are more likely to like intertwine to each other and lock up. So that's going to have more of a frictional force. So that's when it's not moving, it's going to have the static coefficient of friction. But when it is moving, you're going to have the kinetic coefficient of friction. So, if you're already moving, there's not really time for all the stuff to like interlock with each other, all the atoms and stuff. So, the coefficient of friction is going to be lower, and overall there's going to be a lower frictional force. Okay, so, yeah. The above solution is good. But could be enhanced with mentions of the equations for static and kinetic friction. Okay. Yeah. Solution is good. Okay, now we've already been going for about an hour and a half, so I think I'm a call it a stream, even though because scheduling is got to stay on the schedule. Cool. So I'm one moment. So those are all the questions that we are going to cover today. If you enjoyed today's Q&A, I would like to be notified of when we do this next. Please hit the subscribe button below and ring the notification bell if you want to get notified of all of our future uploads. If you'd like to submit your own question, please visit the links in the description below. And remember to leave a like and a comment if you like the video, and share the comment with your friends if you really like the video. This has been Millan with OneClass. I hope to see you soon, and I hope you have a great day and a great evening if it's the evening time. Take care.